Hey y'all, welcome back to another round of astronomy. And yeah, let's get going. Highlighted for you today is that I want to discuss further about naming objects. So let's go ahead and return to our idea about star charts. And as I highlighted for you in the previous video, we adopt the naming convention from the ancient Greeks. Now, the IAU, the International Astronomical Association, formalized this naming convention in the 1920s. Okay? And if you pull up any star chart, you'll see that kind of convention being followed. Incidentally, I'll point out as well, notice that the alpha star is also visually the largest. Down here, they have a scaling about size and brightness. So they use the size of the star to indicate roughly how bright it is. And we'll continue further about what these numbers mean in a later video. Now, there are some problems that we will see pop up every once in a while. And so I'll highlight these for you here. So the first problem is that these observations were made with the naked eye. Okay? And you and I both know that different astronomers are going to have different observations about the naked eye experiment. Okay? So imagine for a second you have two stars that are really, really close in how bright they appear. Astronomer one might come out and say, that star right there, that one's the brighter one, so this one's alpha and this one's beta. But astronomer 2 might come out and say, no, this one's the brighter one. That's the alpha, and this one's the beta. Okay? Naked eye measurements give some flexibility, if you will, or maybe I shouldn't say flexibility, but provide an opportunity for astronomers to disagree about which one's brighter and which one's dimmer. It's not until the 1800s, with the invention of the photographic plate, that we're able to start quantifying which star is visually brighter, which star is visually dimmer, okay? Assigning numbers to it. So there's some problems with these naked eye observations. A second one that crops up that's always interesting is variability. And the ancient Greeks had a philosophical idea. It's that the heavens are perfect. In other words, because the heavens are perfect, there is no change that happens in the sky. If there were a change, that would seem to indicate that the heavens weren't perfect to begin with, right? The heavens shouldn't become more imperfect as time progresses. They should be perfect already. So ancient Greek astronomers did not realize that there's variability in stars. I'll give you an example here. So displayed for you here is a video, and it is of the constellation Orion. The star that I would like you to focus on for a moment is the upper left star. This is a star known as Betelgeuse. You notice it is reddish in color, and I'll let you look at it for a second. Yeah, what do you notice? Yeah. Now, this was an interesting problem. Something happened. Betelgeuse, the star that you see in the upper left-hand corner, suddenly became dimmer. Very odd. And astronomers didn't know what was going on. Okay? Later on, it got bright again, and today it's about as bright as it used to be. Okay? But the issue is that there is variability both in the nature of a star, but also, gases and everything else that's flying around in space. A star that you see today that looks the brightest might not necessarily be the brightest further in the future. Or conversely, a star that is particularly dim today could actually get brighter as it moves through its lifetime. So ancient Greek astronomers couldn't handle this variability. There was a star or two which they labeled as alpha, which later on ended up not being the brightest star. It happens. Another one has to deal with the boundaries of a constellation. Now keep in mind, the International Astronomical Union wasn't formally established until the 1920s, which meant prior to the 1920s, constellation boundaries were neither standardized nor agreed upon. In other words, it's the Wild West. Okay? Astronomers, if you will, could make up their own constellation boundaries. They could publish an atlas of constellations, and people could use them. If you said, yeah, that seems like a good boundary, that constellation you could use. So you have one, for example, Argo Navis. Okay? This was a constellation that was proposed back in the 1750s by a French astronomer. Okay? Now, the issue with this, and again, he published it, disseminated copies of his book. Okay? Some astronomers were using it. But when the International Astronomical Union kind of formalized everything, this constellation was just way too big. It's not very useful for navigating the night sky. So what happened was this old constellation, Argo Navis, was actually broken down into 3 separate constellations recognized by the International Astronomical Union. So you took one big one and made 3 from it: Carnea, Palpus, and Vela. Now here's the issue. Okay? You have Argo Navis, and you've labeled all of the stars, alpha, betas, gamma, delta, epsilon, zeta, yada, yada, yada. You've gone through the whole alphabet, labeling all of the stars in the constellation Argo Navis. Fast forward to the International Astronomical Union, they kept the star labels, okay, and broke apart the constellation. What this means is that between the 3 constellations, Carnea, Vela, and Palpus, there's only one alpha star. I believe it's in Carnea. Another problem, which will be more interesting for the purpose of this course, is that I've been very careful to emphasize the labels were done based on how bright they appear. Not only did the ancient Greeks think that the heavens were perfect, the heavens are unchanging, but they also thought that every star was the same distance away from the earth. You say, why is that? Let's go back to the heavens are perfect. What is the most perfect shape you can think of? Yeah, the ancient Greeks thought the most perfect shape was a sphere. Okay? And so if you have the Earth at the center of a sphere and all of the stars which are located in the heavens, perfect shape. So all of the stars must be located on the surface of a perfect shape, a sphere, which means they're all the same distance away from Earth. So every star is the same distance away from Earth. That means that the brightest star, the star that appears the brightest, is truly the brightest. The second star, the star that appears the second brightest, is truly the second brightest, etc., etc. Okay. Later, in the 1800s, where we'll go at the end of the course, we find out that not every star is the same distance away. And so what we'll end up with is what appears to be the brightest, apparent brightness, and what truly is the brightest, absolute brightest. Okay? The analogy would be this. Say it's your birthday. Happy birthday. And if it's not your birthday, merry unbirthday. So let's say for a moment you have 2 cupcakes. Cupcake number 1, candle on top. Cupcake number 2, candle on top. I take those, I light the candles, and then I move one cupcake, let's say half a mile down the road. Okay? And the question is, which cupcake appears to be the brightest? Yeah, the cupcake closer to you. So the apparent brightness is higher for the close cupcake and is lower for the one far away. Next question. Which candle is truly brighter? Yeah, you say same candle, same brightness. The absolute brightness of the candle is the same. The only reason that that candle appears dimmer is because it's further away. And we'll latch onto that idea. We'll use it later, but figuring out how bright an object is, absolute brightness, and apparent brightness of the object allows us to gauge how far the object is away. Okay. Aside from naming stars, I thought I should also tell you or give you the information about how meteor showers are named. Meteor showers occur very frequently throughout the course of the year, and they originate when the Earth plows through a debris field left behind from a comet. Okay? You say, oh no, do I need to worry about stuff? No. When I say debris field, I'm talking pebbles and little spots of dust left behind as the tail of a comet. This is why it occurs regularly every year, is because the debris field from the comet intersects Earth's orbit at one particular location. And so every year when the Earth travels around in space and gets back to that position, that debris field, it sweeps back through. Now, the naming convention for meteor showers. You go out at night and you look up and you see these meteor showers coming in at you. Okay? The location in space from which the meteor showers appear to originate is called the radiant. Okay? And the trick is, a meteor shower is named after the constellation from which the radiant appears. So, number 1, locate the radiant. Where in space do these meteor showers appear to originate? Number 2, identify the constellation. And then number 3, add like IDS on the end. Okay. So, for example, the meteor shower Oranids, Oranids appear to originate in the constellation Orion. The Taurids appear to originate in the constellation Taurus. The Geminids appear to originate in the constellation Gemini. So again, by memorizing the star chart, you'll hear these names pop up, and you should hopefully be able to navigate to where you should be looking. Okay. Good? Cool. I thought I would give you at least one instance where that is not the case. And again, this comes back to the constellations and the naming conventions and la 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 la. Okay? And that is the quadrantids, which occur in early January. Okay? Now, the quadrant Muralis was again a constellation which was proposed by a French astronomer roughly around 1800, so the turn of the 19th century. When the constellation boundaries were formally introduced, the quadrant Muralis went to the wayside. It's no longer in use. Rather, it's the constellation Bootes, or I can't remember if it's Bootes and Draco, the dragon. Okay, But that quadrant Muralis is no longer in use as a formal constellation. But the meteor shower is still named after it. Okay? So the meteor shower didn't get renamed. They kept the old name, Quadrantids, but then they got rid of the constellation. So it's one of, again, it's that it was an arcane constellation, but they kept the name of the meteor shower. Pretty cool, huh? Okay, some practice for you. Boom. Identify the alpha star in this constellation. You got it? Yeah, good, good, good. Pause the video if you don't. Okay. And again, even if they don't label them on a star chart, for example, for visual clarity, they will usually change the size of the star. Okay. So a larger star is supposed to be indicative of brightness. So here, Aquila, we have the bright star right there. Okay, that's the alpha star. And then you can get an idea. Now, the beta star is going to be hard because it's either that one, it's probably this one right here. You could argue this one or maybe that one. Okay? So it gets a little tricky sometimes. But certainly in this case, you can tell me the alpha star. Okay, good, 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 good. Other question for you. Okay. Go ahead. Where's the radiant located? You got it? Yeah, good, good, good. So again, you get a demonstration of kind of visually how you do this. You take a time-lapse photograph, and again, you see these pieces of dust striking the upper atmosphere. Now, yeah, you get a couple that are kind of cockamamie in some weird direction, but by and large, most of them you see are pointing back to somewhere around here. Okay, somewhere in that part of the sky is the radiant. And then we would have to go and see what constellation that is. I believe that this is a picture of the Geminids, although I'll have to double check. Okay? Good? Sweet. So I'll leave it there for the naming conventions, and we'll continue on our merry way. I thank you for your attention. Keep up the good work. I'll see you next time.